An LC circuit can store energy in two places: in the electric field between the plates of the capacitor and in the magnetic field inside the coil of an inductor. So the total energy of the system would be the sum of those two. Now, the energy in the capacitor varies with time because the charge on the plates varies with time, and the energy stored in the inductor varies with time because the current here varies with time. So, what about the total energy of our system? We have these two sinusoidal solutions for the charge as a function of time and its derivative, the current as a function of time. Comparing these and knowing that the current is the derivative of the charge on that top plate, we see that taking the derivative here, we would pull out an omega, so Q times omega is our max current, I. So our max current is omega times the max charge on that top plate. Omega, we've seen, is equal to 1 over the square root of the inductance times the capacitance. And so we get this relationship between the max current and the max charge on our top plate. So I can use this to simplify our expression for the total energy here. I've taken this function and plugged it in for Q of t, and taken this function and plugged it in for I of t to get this total time dependence for the total energy. And now here for the total current, here for the max current, I'm going to sub in this expression. So putting that in there and squaring it, I see that the factors of L here and here will cancel. And we have 1/2 1 over c times q squared, and here 1/2 1 over c times q squared. So I'm going to factor that out of both of these terms. Factoring that out, we're left with cosine squared omega t plus sine squared omega t. And by our Pythagorean trig identity, that is equal to 1 for all time. And so we're showing here that our total energy is just equal to this expression, 1/2 1 over c times the max charge squared. The time dependence has disappeared. We've proved that our energy is indeed constant. The energy is conserved in a simple harmonic oscillator. And if we again use this relationship, we can replace Q with I here and show that the total energy is also equal to this expression, which is telling us that there is a moment in time when all of the energy is in the capacitor, and then later, in fact, exactly 1/2 cycle later, all of the energy will be in the inductor. So we can express the total energy in terms of the max charge or in terms of the max current. Okay, I want to think more about this circuit as an oscillator and compare it to another oscillator that we're familiar with, a mass spring oscillator. So if we consider a horizontal mass spring oscillator on a frictionless surface, the total energy of that system is equal to the spring potential energy plus the kinetic energy of our block here of mass m. In our mass spring oscillator, this spring potential energy, depending on position x, is analogous to the energy stored in our capacitor in our LC circuit, which depends on the charge on that top plate, Q. I say they're analogous because we've got one form of energy that depends on x, depends on Q, and then another form of energy that depends on the derivative of that variable. Here the kinetic energy depends on dx dt, and here the energy stored in our inductor depends on dq dt. So the current here is like analogous to the velocity of our block, and the energy stored in our inductor is analogous to the kinetic energy of our block. So from this point of view, our capacitor is kind of like our spring storing potential energy, and our inductor is kind of like a thing storing the kinetic energy of the system. And throughout a cycle, throughout an oscillation, we're transferring energy back and forth between this potential-like form and this kinetic-like form, just like we are here. Let's look closer at these variables. We see that the mass here is playing the role, or inductance here is playing the role that the mass does here. Those are both representing the inertia in the system. The factor in front of the time derivative squared factor, there is our inertia, that resistance to changes in. This is resisting a change in velocity. This is going to resist a change in current. And our other coefficient. Here, the spring constant K is analogous to 1 over the capacitance. So we see here that a system with a stiff spring, a large K, would be analogous to a system with a low capacitance, and vice versa. A soft or loose spring with a small K would be analogous to a system with a high capacitance. So if you got a high capacitance, that's like a loose spring in that you can store, let's see, it takes more time to compress and stretch a loose, soft spring. It's sort of slower to respond if you got a soft spring as opposed to a stiff spring, which will respond much more rapidly. So a soft spring is like a system, it's like a capacitor with a big capacitance where it has so much capacity for charge that it takes a long time to fully charge it up, then a long time to fully discharge it. That's the comparison there. Okay, so we set up our LC circuit by having our capacitor initially fully charged. That's like pulling our spring out to its max extension to a displacement from equilibrium x equals a, the amplitude of our resulting oscillation, and releasing it from rest right there. So our velocity here is 0, just like our current here is 0. So these are the sort of comparable starting states. Then 1/4 period later, the mass has moved here, and our capacitor has fully discharged, and we've converted all of this stored energy in the capacitor to stored energy in our inductor. Here, we've converted all of our spring potential energy into kinetic energy. Another quarter cycle later, we've converted all that kinetic into spring potential, and here we've converted all that energy stored in the B field in the conductor back into energy stored in the E field. Sorry, this is the energy stored in the B field in the inductor, back into energy stored in the E field in the capacitor. Although now, compared to originally, a half cycle later, the energy is back in the electric field, but with reverse polarity. E field is up instead of down. Likewise here, our energy is stored in our spring. Once again, we're back in spring potential energy, but we're at maximum compression instead of maximum extension. Then another quarter cycle later, we've got the energy back in kinetic form over here, or back in our B field over here in our kinetic-like energy. And then after that, we return to our original state here. So we see our cycle completes for both systems. One more comparison, let's go to the dynamics. From Newton's second law, we get this expression for the relationship between we get this expression that represents simple harmonic motion for our mass spring oscillator, and recognize that this combination K over M, that's our omega squared, which gets us the period mass relationship for a mass spring oscillator. Likewise here from our Kirchhoff-Faraday law, this is the form of simple harmonic motion, so our omega squared is 1 over LC, so we get this period relationship for LC. So when I have capital T for the period here, this would be the period for our mass spring oscillator, and this would be our period for our LC circuit. Okay, so I hope the interpretation of our circuit is a little more concrete to you now that you can make this comparison to the mass spring oscillator. Okay, well, I've got one more thing to discuss, and that is what happens if we add in a resistor to our LC circuit. We call this an RLC circuit. So this would be a more realistic scenario. This is a non-ideal case. Any real wire is going to have some resistance in it, so we expect an actual oscillator to include this. So if we have that, the RLC circuit, what's the additional effect we get? Our Kirchhoff loop equation, if we define counterclockwise to be the direction of a positive current, and going counterclockwise, we have this equation, minus L di dt, then minus Q over C, and then minus IR going through our resistor. So here's the additional term we get from our resistor. If I rewrite this equation in terms of Q, I is dq dt, and di dt is d squared q dt squared. So we see that we've got an equation here that involves q, the first derivative of q, and the second derivative of q. This term involving that first derivative that appears if we have resistance, that is what's known as the damping term. That is going to cause our harmonic oscillator to have a damped behavior, a damped harmonic oscillator. Because this equation is a differential equation that involves the second derivative of Q, it's also known as a second order ordinary differential equation. I'm not going to fully solve this right now, but we can sort of predict what the outcome is going to be. We know our resistor is going to be converting energy into heat over time, so the mechanical energy of our system is going to be decreasing with time due to the heat losses here. So if the total energy of our system can be represented as 1/2 1 over C times the max Q squared, or 1/2 times the inductance times the max I squared, we know that if E is decreasing with time because of the heat losses here in our resistor, that means the max Q must be decreasing with time. Over subsequent cycles, we should have less and less maximum charge on our capacitor. Likewise, we should be hitting a lower and lower maximum current on successive cycles. And so our charge on our capacitor versus time behaves like this. The max Q is decreasing with time, so we have a damped oscillation. If the conditions are right, we get what we call an exponential decay-like envelope here. So you take our sort of sine function and squeeze it inside these two exponential decays to show our amplitude decreasing, decreasing, decreasing with time due to our damping here. That's the way any realistic system will behave. It will cycle back and forth, but over time those oscillations will get smaller and smaller, and eventually all the energy stored in our capacitor here will be converted into heat. Much like you'd expect from an actual mass on a spring oscillating back and forth on a surface that has friction, over time those oscillations damp out, and all the energy eventually gets converted into heat via friction.